Alright, gang, here we go. This is for Chem 2, Unit 7. We're talking about kinetic molecular theory, effusion, and diffusion of gases. Pretty sure that's it. Should be a fun time. Alright, kinetic molecular theory. So, just briefly, just to remember how things are going here, just basic science stuff. Alright, laws, okay, tell us what happens in nature. Okay, so specifically, we've been talking about all these gas laws: ideal gas law, Boyle's law, Charles' law, all this stuff. And so this tells us what is going to happen based in certain conditions. Okay, now in order to explain why those things happen, we develop theories. Okay, so laws tell us what is going to happen. The theory is our explanation as to why. So laws generally don't change. Okay, pretty constant. That's why we call them laws. And then theories, though, can change based on new evidence. Okay, and so that's essentially what scientists do: is develop theories to explain the laws. Okay, anyway, so kinetic molecular theory has main tenets here. Most of this should be review from Chem 1, but let's go over them. Okay, so essentially we've got 5 tenets of kinetic molecular theory that you need to be familiar with. Okay, number 1, gases consist of a large number of molecules that are in continuous random motion. Okay, so gas molecules bounce around like crazy. They're bouncing off each other. They're bouncing into the walls. Okay, and there's so many of them, and that makes sense because they're super tiny. Okay, the combined volume of all the molecules of the gas is negligible compared to the total volume in which the gas is contained. Essentially, what we're saying is that they're really far apart from one another. Gas molecules are insanely small, okay, and then the container they're in is insanely large. Okay, so essentially, if you took all of the gas molecules and compressed them down until they were solid, that their volume would be negligible compared to the volume of the container that they are inside of. Okay. We also assume, based on the kinetic molecular theory, that attractive and repulsive forces between gas molecules are negligible. So if you've got 2 gas molecules, there's no intermolecular forces keeping them together, no polarity or anything like that keeping them attracted to one another. All right. Number 4, energy can be transferred between molecules during collisions, but the average kinetic energy of the molecules does not change with time as long as the temperature of the gas remains constant. Okay, so average kinetic energy over time is going to remain constant, but individual molecules can go faster or slower depending on what they've hit, how they've hit, so on and so forth. So imagine like a frictionless pool table. You hit those pool balls. Some of them are going to bounce, really fast at first, and then they might hit something that makes them stop until they get hit by something else. Gas molecules essentially do the same thing. And number 5, the average kinetic energy of the molecules is proportional to the absolute temperature. Okay, so essentially what we're saying there is kinetic energy indicates the average temperature. Okay, or so we can really measure the average temperature of our whatever it is, and that will tell us the average kinetic energy. All right, those two are proportional to one another. Okay, so how fast do molecules move? Now, this is kind of an idea. All right, we're going to these get graphs up here. These graphs are bell curves showing you they're not perfect bell curves, obviously, but they're showing you the relative amounts of molecules moving at specific speeds. So this blue bell curve, this is at 0 degrees Celsius. All right, and we're saying that the vast majority. Okay, so you think about the area under a curve. Okay, the vast majority of your molecules are moving about this fast. Okay, and as you get faster here to the right, you get fewer and fewer molecules. This fraction goes down. Okay, and then at 100 degrees Celsius, notice that the area under the curve is exactly the same. Like if you added up all these boxes and added them up, they would be the same number of boxes under the curve as the blue. However, it's spread out more because you've got more energy, so that average has moved to the right. All right. So temperature is related to the average kinetic energy. Individual molecules can have different speeds. We just explained that. Okay, so we have 3 different speeds that we care about. One of them is more important than the others. Okay, so the UMP is the speed, and for whatever reason the textbook uses U for speed. So UMP is the most probable speed. Okay, so it's the speed exhibited by the largest number of molecules. So essentially it's whatever the peak is. All right, that's your UMP. Okay, the UAV, all right, is the average speed of the molecules. is the average speed of the molecules. All right, so if you went and you actually calculated the mean, sum them all up, divide by however many there were, that would be, you would get this value right here, this UAV. All right, okay, or the X value related to that, so down here. But whatever. And then URMS, okay, now this is the important one chemists care about. Okay, URMS is the root mean square speed. All right, it's the one associated with their average kinetic energy. All right, the root mean square speed. Okay, so, and we'll show how to calculate that here in a minute. But this is the one that's actually associated with their kinetic energy. All right, so that's the one that chemists really care about, because we really care about that kinetic energy because we can measure kinetic energy via temperature, and so it kind of makes sense as to what's going on. All right, so URMS. Okay, and the molecular mass. At any given temperature, the average kinetic energy of the molecules is the same. That makes sense, right? Because that's what temperature measures, is the average kinetic energy. All right, so 1/2 of the mass times the URMS squared. Okay, now this is the same formula as kinetic energy, right? Because kinetic energy is equal to 1/2 mv squared, right? So you got the mass times the velocity squared. URMS is our velocity, right? It is the same for two gases at the same temperature. That makes sense. It's essentially the same thing as what we said right here, all right? If a gas has a low mass, its speed has to be greater than for a heavier molecule. And that also makes sense, right? If the kinetic energy is the same, but your mass is a lot bigger, that means your velocity had to be smaller, right? And if your mass is a lot smaller, that means your velocity had to be a lot bigger. And we can do a little bit of finagling here with our math. Okay, and we get this formula here to actually calculate your URMS. It's equal to the square root of 3 times our R value times T divided by capital M. Remember, capital M here is the molar, okay, the molar mass. All right. So at the same temperature, here at this graph, we're all at the same temperature, but notice how the lighter the molecule is, the higher their URMS value. Remember, the URMS value was about here on each of these curves. Notice that oxygen moves significantly slower. Their URMS is significantly slower than for hydrogen. Hydrogen's URMS is probably somewhere around here, and it's, 4 times faster than the average oxygen molecule. Okay, or has 4 times the kinetic energy. No. The same kinetic energy, it's 4 times faster. I said it right the first time. All right. Okay, so applying the kinetic molecular theory, it says a sample of O2 gas initially at STP is compressed to a smaller volume at constant temperature. What effects does this change have on the average kinetic energy of the molecules? Well, if you're still at a constant temperature, it might be compressing, but it says that it's staying at a constant temperature. That means the average kinetic energy has to remain the same. Okay, so the kinetic energy is unchanged. That was easy. All right. B, their average speed. Well, if their kinetic energy remains the same, remember kinetic energy is calculated by 1/2 mv squared, so that means that speed, okay, UAV, unchanged. All right, that makes sense. Okay. C, the number of collisions they make with the container's walls per unit time. Well, if it's being compressed, that means they have a smaller volume, so it makes sense that they would hit the walls more often. Okay, so collisions would increase. Okay. And the second last one here, D, the number of collisions they make with a unit area per with the container walls per unit area of container wall per unit time. That would also increase. It seems silly. Okay, so it's essentially the same as D. All right, but I guess it's for a specific area. It seems redundant. Whatever. All right, E, the pressure. Well, if the number of collisions are increasing, therefore the pressure has to increase as well. Okay. Effusion and diffusion. All right. Effusion is the escape of gas molecules through a tiny hole into a completely evacuated space. All right, so this is essentially like if you get you're in the space station or a space ship, right, and you get a tiny hole in it, and then your gas starts leaving. Your gas is effusing. Okay, diffusion is the spread of one substance throughout a space or a second substance. Okay, so this is if you let some let some gas off, right? You have a little toot, if you will, and then it'll spread out throughout the room, right? So it's going to spread out over the room. So that's a diffusion. So gases effuse if they go through a tiny hole. They diffuse if they're just spreading throughout another second substance. Okay. So Graham's law of diffusion and effusion gives us an idea of how fast this will happen. Okay, so it relates, and it's really nice, and we're not going to derive it because it's kind of a pain in the neck. But anyway, it relates the molar mass of the gas to their rate of travel. Okay, and this makes sense because we just talked about how at a certain temperature, all gases have to have the same kinetic energy because they're all at the same temperature. Okay, and we just said that the heavier they are, the slower they have to go, so their kinetic energy remains the same. We're just playing on that idea a little bit more here, and we're just saying that, well, a lighter gas would have to go faster than a larger gas in order to have the same kinetic energy, and we end up with this interesting ratio here. Okay, where the rate of speed of the first gas over the second gas is equal to the square root of the molar mass of the second gas over the first gas. All right, so this is an important equation that I want you to be familiar with. All right, I also like this graphic here. Notice how you've got two balloons, argon and helium are filling these two balloons. Now over time, because helium is lighter, has a smaller molar mass, it will effuse out of this balloon a lot faster than the argon will. So you can tell that the helium over time has starting to go out of the balloon. Okay, and the argon will also effuse over time as well, but it's going to happen a whole lot slower because it's got a larger molar mass. Okay. So last thing here, we're just going to calculate the ratio of effusion rates of N2 gas versus O2 gas. All right, so we want the rate of N2 versus the rate of O2. Okay, so, and Graham's law just told us that it was the square root of M2 over R1. Okay, so it would be the square root of M of O2 over M of N2. Okay, so it would be the square root of molar mass of O2 is 32.00, and the molar mass of nitrogen is 28.02. All right. So we can take the square root of 32 divided by 28.02. We get 1.07. Well, that's not self-fig, is it? 1.08. 1.069. 069. All right. So that's the ratio of the speed of nitrogen versus oxygen. All right. So that's not too bad. Anyway, do your homework problems. Let me know if you have any questions, and I'll see you on the flip side.